Hi, so something a lot more practical today. We're going to be talking about search space in relation to brute force methods. And I hope you already have an idea what a search space is. To me, a search space is just a set of all possible solutions. So I got a problem, and I have to look for the solution, and where do I look for? The search space. Like I look at all the possibilities. Some people say that I can only use this term if I'm talking about the search algorithms. And to me, I don't really want to talk about the definitions. I don't want to argue about the definition, so I'm just going to use search space. Even if I have a optimization problem, or even like a decision problem, I'll still say I have a search space. I can always use the word solution space. Some people also say that, well, if you say search space is a set of all possible solutions, then what about the impossible solutions? Again, I don't want to argue. Just use some common sense when it comes to these definitions. All right. If you do have a problem with the definition, you can let me know and we'll try to fix it. But otherwise, I don't think it's important enough. I mean, if you use the word search space or solution space, people will understand what you're talking about anyway. So what do I mean by impossible solutions anyway? This came from a conversation a while ago when I had the example about looking for an element inside an array. So I claim that if I'm looking for an element, then the search space is the whole array itself. Like, let's say I'm looking for 8, right? Then my search space is the array 3, 5, 7, 8, 10. And then the question was, well, if you're looking for 8, then the only possible solution is actually 8, right? So all the other guys, 3, 5, 7, 10, they're impossible. Like, they're not the solution. So why are they part of the search space? And my answer to that is, well, you're actually looking at it the wrong way, because the search space here, I'm not talking about the numbers, I'm talking about the index. Like, my solution can either be index 0, index 1, index 2, or index 3, or index 4, one of them. So I have to go through all of them, right? So can my answer be in all of them? Yes. Can my answer only be in one of them? Yes. And so the whole array is my search space. So I hope that is also obvious when we talk about knapsack, traveling salesman, all these MP problems. Because with these guys, there are so many combinations, and not all of them will be a solution. Well, maybe one is the only solution, maybe some will be solutions, but solution space, search space, they look a lot more obvious when we talk about these problems. Okay, but again, don't want to get too fussed about definitions. So when you think about search space, I'm sure we think about the same thing, right? The all possible solutions, what are the possibilities, what are we looking for, what are we searching through, that's the search space. So today we're going to talk about a few things about search space. For example, we're going to talk about how to construct the search space, we're going to talk about traversing a little bit, and to do so, I'm going to use an example. Well, this is the main example that we're going to be using. It's about rod making. So the problem is I'm going to give you a bunch of rods of different lengths. Like, let's say I have different length 10, 12, 5, 7, 11. And I'm going to ask you, can you make a rod of certain length? For example, can you make a rod of length 22? And yes, it's going to be yes. You just take one which is size 10, the other one which is size 12, you're done. Can you make a rod of length 9? And you won't be able to, because you can't cut them up, right? And the smallest is 5 or 7, and that won't be able to make a 9. So a pretty simple problem, I hope. And here what I'm doing is I'm going to formalize that a little bit, because I will say that when you have a problem, think about the input and think about the output. If you can, try to give names to them. So that's what I'm doing here. The length that we need is going to be L, and I also have to input the array containing the lengths. So I specify that those are the inputs, and the output is going to be yes or no. So notice that this is actually a decision problem, as in you just say yes or no, and it's still relevant for me to talk about search space, as we will see. I can also go a step further and try to define the problem more mathematically. So here I use some mathematical notation. I say that the array containing the length is the array B with B1, B2, bn. So if I have n rods, and also have an integer L, which is the length of the rod that we need to make. Then I'll say the output is true if there's a subarray bi0, bi1, . So these I0, I1, they're just subscripts, right? meaning that I will choose some, maybe all of the rods in the set B, right? And when I add them up, I will get up to L. So when I add up all the length of the rods that I choose, I will get L. And that is exactly the problem we're trying to solve, right? Now, one thing you may ask is, do we need to specify problems in a mathematical way? And my stance on this is you don't have to, but if you can, that'll be great. The problem is, if you're using English, sometimes it can be ambiguous, right? And if there's some ambiguity, I may have to say that this is incorrect. But on the other hand, if you're trying to use math, but you don't actually know what you're doing, that's bad as well. So use English if you are more comfortable with English. That's completely fine. And I think in most cases, it's not going to make that much of a difference anyway, right? But if you can use math, you're okay with math, then go for it. It'll be a lot more clear. All right, so that's just a quick aside. Okay, let's go back to the problem. So that is a sample input that we had earlier. And if L equals 25, we say there's no solution. If L equals 22, there should be multiple solutions. At least there are 2, 10, 12, and 10, 5, 7. So you should be able to recognize that the search space has 32 combinations, 2 to the 5. Now the question is, how do we actually find all of them? Some students I saw in the past, when they look at this question, they want to make a nested for loop right away because they got 5 elements and, well, I have to try every single one of them, right? So I'm going to make 5 for loops. But what if your input has 100 elements in it? You're not going to be making 100 nested for loops, right? So this is definitely not the right approach. You don't use nested for loops like that. The right approach is to use recursion. So that's what we're gonna do. But before we go look at the method, I want you to think about problems and subproblems. So whenever you solve a problem, I want you to realize that you're actually solving it by breaking it down into small subproblems. I mean, we probably already talked about this in previous subjects, but just in case you don't see it that way, I want you to start seeing it like that. Let's say you have an array and you're searching for one element inside the array. Your original problem is, here's an array size n, go look for this element. Then you look at the first element. Let's just say you're doing linear search. You look at the first element, and that's not the element you're looking for. So now the problem becomes, here's an array size n minus 1, go look for the same element, right? So you have a you have a problem, and you reduce it down into a small subproblem. And this is what you do. You keep on reducing it down. If you have a for loop, you have an array size n, then it becomes n minus 1, it becomes n minus 2, n minus 3, and so on until eventually you got nothing left in the array, right? Okay, you keep on reducing the problem into smaller and smaller and smaller subproblems. If you can recognize the subproblem, it will actually help you in constructing the search space. And this concept here, we're going to look at again next week, but since we're gonna see it also this week, well, I might as well mention it now. Okay, so with the rod making, what are the problems and what are the subproblems? So the original problem is I give you an array of 10, 12, 5, 7, 11, and I ask you, can you make 25? Let's say that's our problem. Then if I reduce this into subproblems, I can have several actually. I can pick 10 now. So if I pick 10 now, I'm gonna have 12, 5, 7, 11 left over, and I have to make 15. If I pick 12 now, I have to make 13, and I have those 4 rods, 10, 5, 7, 11 to choose from. Same thing if I choose 5, or if I choose 7, if I choose 11 now. So I can choose either one of the rods, and I will end up with a subproblem. So I can draw it like this, right? You have the original problem up there, and it branches out to 5 different problems, and each with a different set. Like you have a different input, right? Different arrays and different L. Okay, so that is how you break down a problem into subproblems. Now, how do you actually write the code? So I have like a skeleton here for the code. I'm gonna call it solve, and the input is gonna be the array in I, which is the index. Actually, I'm not sure how I'm gonna use I here, but because the code is incomplete anyway. Right, I want you to think about how to actually complete this code. So you will stop when L is equal to 0, because that means you have made the rod of length L. You also stop when b.length equal to 0, because I guess I'm trying to say that if you don't have any more rods, you can't make the long rod. But the for loop, you're gonna have a for loop because for each problem you're gonna have to go through each element and pick one, right? So you're gonna have a for loop here, and I want you to have a think about how to write this, but just don't actually write it down, just have a think, because this is not how we're gonna do this anyway. This is actually the wrong approach, and I'll show you why. When you making a subproblem out of your original problem, you actually have two options here. The first option is what I described earlier. So you pick one element and then you start recursing. So you have 10, 12, 5, 7, 11 to choose from. You pick 10, then recurse. Or you pick 12 and then you recurse. And so on. This is the second option. Instead of picking an element in the array, you choose the index to, or at every index, you either choose the element or you don't choose the element. So when I start the problem, I start with the first element, which is 10. I can either choose to pick it or I choose not to pick it. And then after I do that, I choose either to pick 12 or not to pick 12. I hope you can appreciate why this is different, because with the first approach, when I break down the problem into subproblems, I have 5 options. But this time around, I only have 2 options. Either I pick 10 or I don't pick 10. So now my diagram will look slightly different, right? Before, from the first one, I have 5 arrows going down, and now I only have 2. And on every level, actually, whenever I have to make a decision, I only have 2 choices to make from. Right, so we can see that the first level here, the first choice we make, it concerns 10. The second level, it concerns 12, and then it concerns 5, and then it concerns 7. Right, so this is a different way of doing it. And as you can see, which one's actually better? So the top one is the second approach. The bottom one is the first approach. So you can see that with the bottom one, it's not like you go 5, 5, 5, 5 all the time. On the first level, you have to do 5. And the second level, you only have 4 to choose from. And the next level, you got 3 to choose from. But there is a lot more arrows. So how come the first one is much better? You should be able to recognize that the top one, you only care about combinations. Because if I give you an element, you either choose it or you don't choose it. With the bottom one, you actually care about the order as well. Because if I pick 10 and then pick 12, I'll be going to, let's say I'm going up here, then I go down there. Then I will pick 12 here. So one of the cases here. I will end up with 5, 7, and 11. But that's the same thing as me picking 12, right? Going down there, and then picking 10. If I go down somewhere down here, I will also have 5, 7, 11. So the first approach that we did, was actually wrong. Well, it's not wrong. It's just that you're counting permutations as well, which is not what we want, because all we care about is the combinations. So that is a very important thing when you're doing brute force. Make sure you understand whether you need permutations or when you need combinations, right? And the criteria are simple. Does the order matter? In our case here, does the order matter? No, it doesn't. We only care about combinations of rods of certain length. And this can be quite tricky, actually. I see people make mistakes all the time when it comes to choosing permutation or combinations. Let me give you another example. So this one here, I want to produce all possible combinations of 3 unique letters in the alphabet. So I want ABC, I want ABD, ABE, AYZ, then BAC, BAD, and so on. Right? All possible combination of 3 letters, and just 3 letters. Not 1, not 2, not 4, but just 3. How would you do this? What do you think about this? So here I can either choose A or not choose A. After I choose A, I can either choose B or not choose B, choose C or not choose C, and so on. So I end up with all combination of 3 letters. Is this what I want? Well, if I look at the question again, no, because I actually want BAC here, right? And is there any way that I can generate BAC here? Well, no, because as soon as I choose B, I can go back to A. So I got B here, I can only go to B, C, and so on. So if a character occurs, then the next character after it must be greater. Okay. And so the problem with this question here is that instead of using the word combination, this really should be permutations. But this happens quite a bit in real life. Sometimes when you want permutation, you say combinations anyway, combinations of everything. Why? Because we don't use the word permutation that often. Well, general people, lay people, they don't use the word permutation that often. They sometimes say combinations when they actually mean permutations. When you get a question from me, I'll be clear whether I want permutation or combinations. Although actually it will be you who has to decide whether you want combinations or permutations. So careful with that. What else we have to say about? Oh, okay, sorry. So this is the wrong way of doing it. This is the right way of doing it, right? So instead of just having two choices on each level, like yes or no, here you go, well, I can either choose A, B, C, D, or up to Z, and on the next level, I can also choose A, B, C, D, up to Z, or whatever. Is this okay? Looks much better, yep. Well, actually, there'll be only 3 levels, because you only have like 3 character words, so you only need 3 levels. Well, this again is still wrong, because what do we want? We must have unique letters. We can't have AAA. And this one here, I will have AAA. I mean, that's a possibility. So again, this is actually the right one. Like this. So you have 26 choices on the first level, you got 25 choices, and then 24 choices. So notice that all of these are just trees. In fact, maybe I think I already used the term subtree before. I call something a subtree or something. Anyway, well, there are obviously trees. I call them decision tree from time to time because those diagrams, those trees tell me what decision my program is making or what decisions are available to my program at that point, right? So if I can draw this tree, it kind of illustrates what decision I have to make. It makes it clear. So I like drawing these kind of things when I'm solving a problem. And also, most importantly, you can see the breakdown between problems and subproblems when you do this. We'll talk about this more next week when we talk about dynamic programming. But for now, is it always a binary tree? No. As we can see, it's not. It can be a tree with many children, like this one. So this is yet another problem. Generate all possible license plates. Right? So very similar to the one before, but this time you're allowed to have duplicates. Again, be careful with how you make your trees. Okay. So, how do you go to your sample solution space? Easy. It's just traversing through a binary tree. So it's a good thing that you've, well, not a binary tree, just traversing through a tree. So it's good that you've done trees in COM 25, COM 2010, right? Because we going to be using whatever you learned back then. Let's go back to our main problem here, the rod making one. All right. So if you remember this this decision tree. So from the original problem, I either pick 10 or I don't pick 10. I pick 12 or don't pick 12, and so on. This is what the code looks like. So I'm going to call this solve, right? I'm going to have an array B, which contains all the different lengths. I have integer I, which tells me which array index I'm at the moment. Like, am I choosing to include 10 or not? Am I choosing to include 12? Am I choosing to include 5? So that is controlled by this I here. So I can be 0, 1, 2, 3, all the way up to b.length. Because when I get to b.length, that means I'm finished. I don't have any more rods to choose from. And L here tells me how much length I still need to make, right? So when I first start off with this example here, L will be equal to 25, right? And I equal to 0. So what I'm doing down here, I'm deciding whether or not I'm going to include 10. So if I include 10, I'm going to reduce L by 10, which is bi, like b0. If I don't include 10, I will keep L as it is. In both cases, I will pass b to the next recursive call, and I will pass I plus 1 to the next recursive call because that's saying that I'm done with 10, now go process the next element, which is going to be 12. All right. So hopefully that code makes sense. This is the simple combination code. This is a form that you should use most of the time. If you want more practice in coding this kind of code, then the best option probably is go to Coding Bat. They have the recursion 2 subsection here. This is all about brute forcing. Well, this is called about recursive backtracking, which is exactly what we need. I'm probably going to put one of them or 1 or 2 of them in the workshop exercise for this week. So those ones, you should give it a try because this is coding. and it's going to help your assignment as well. So yeah, probably a good idea to give them a go. So anyway, hope that code makes sense. I explained that pretty quickly, but it's not that much to explain really. This is just you can think of it as like a binary search traversal, right? So this is like going left and it's like going right. Either I pick the current element or I don't pick the current element, and that will affect L. And B and I, it's just the same. Okay. So when you look at the code here, something I want to think about is how are you traversing it here? Are you doing DFS or are you doing BFS? So think about tree traversal, think about post order, in order, pre-order traversal that you did in COM25, COM2010. Are you doing DFS or are you doing BFS? Let's see what happens. I'll start from top here. Okay, I'm going to recurse to the left. B, I plus 1, L minus BI, so that means I choose 10. And then what do? You will recurse to that function, so you'll arrive at the stage, you will recurse to the left again, because you will pick 12. You will always go to the left-hand side. Before, when you backtrack, when you finish, you go back up, then you do the OR operation, and that's when you recurse to the right. So you will always go deeper and deeper and deeper first. This is DFS. Same thing here, right? When you're making these 3-letter words, which was the wrong solution, by the way, but this will make all 3 possible combinations. How do you do it? You go left first. Bang, bang, bang. ABC. Then you make ABD, and so on. This is again DFS. And we use DFS almost all the time because that's more natural. This is how recursion work. Okay. And remember that with DFS, what we want to do is we want to make with brute force, what we want to do is we want to make all bit string of certain length n, right? Something like this. Like you have like let's say you got 5 items to choose from. You want to make everything from 0, 0, 0, 0, 0 to 1, 1, 1, 1, 1. And we build our solution incrementally using DFS. So you go from 0, 0, 0, 0, 0, 0, 0, 4 zeros, and let's say n is equal to 4. That's as much as you can go. You backtrack and then you make 0, 0, 1. Right? Because why? Because this minimizes the work that we have to do. Like if you want to build 0, 1, 1, 0, if you want to build, actually this is the other way around. If you want to build 0, 1, 1, 0, 1 from 0, 1, 1, 0, 0, the best way to do it is just to backtrack to 0, 1, 1, 0 and then go to the right and add 1 to it. And there, I just fixed it. Okay, so now I think that's the right sentence now. Yep, that's correct now. Okay, so backtracking, we'll talk more about this next week. But you already know how to do this anyway, I hope. So as I said, this week's going to be pretty easy, pretty chill, not much to do. Just make sure you practice how to do the recursive backtracking. And also your assignment, which is again just brute force. I may make a video about the assignment. We'll see. But anyway, today we've done, what have we done? We talked about constructing search space. We talked about problems and subproblems. We talked about decision tree and how to traverse through that decision tree. This second one here, problems and subproblems. I hope you can see how we have always problems and subproblems when you're making that decision tree. And keep this one in mind, keep this topic in mind, because this is going to be a lot more important next week. We're going to break down problems into subproblems, and actually in the next few weeks. And it's going to be a very important concept, and yeah, you'll see. Anyway, that's it for the lecture. I'll see you again in the next one.